Welcome to my new YouTube channel called the Tipping Sliding Mass Problem. Okay, so I'm still working on this. I was going to do the spring model of this. So if you're just joining, I wanted to model a stick tipping over, and so I did that, the pivot like that, and then I did it by modeling this as a spring. I did that, and then I did this allowing for the base to slide, and thanks to user William Perez Hernandez, who found my error. I did make an error, even though it looked like it worked out okay. And it was pretty close. I was pretty close to getting it right. Okay, so here is my error. So let me tell you what I did. Link to the whole playlist below. So I want to model this system. So there's two masses right here, and this one can slide on the frictionless table, and this one can fall over. And so I model that with the two generalized coordinates theta and x to describe the system. So I get the kinetic energy in terms of x2 and y2, the values up here, and the x value for that one. And everything's good. Now I get the Lagrangian. I use the Euler Lagrange equation to find the equations of motion, and I did that. Now here, I think here was I made my mistake. Yeah, so I did it for the generalized coordinate for x. I did the generalized coordinate for y. And so this has x double dot, so it's meters per second squared. And this is wrong. That's not meters per second squared. That's meters per second. So there's an error right there. That's where my error is. So where did I get the x double dot? Well, anyway, there's an error. So I'm just going to start over. And since I'm starting over, I'm going to do what I should have done. And what I should have done was to not assume these are the same mass. If I do that and I get an equation of motion for different masses, I can make this mass very, very, very large compared to that one, and it should be back to the pivot problem, or at least close. And that's a great way to test the solution. Okay, so let me show you what I have so far. So here's x2, y2. That's the x and y coordinate in Cartesian coordinates for this. I need that because I can take derivatives in the Cartesian coordinate system. So I'll take the time derivatives to get the velocities, square that to get the kinetic energy. This cosine squared, sine squared term cancels, and I get that for the kinetic energy. Notice this is m1, that's down there, that's m2 up there. And that's the potential energy. It only depends on m2 because this one is at y equals 0. And then there is my Lagrangian right there. And I think that's right. Let's just check. So these should all have energy terms. That's kinetic energy, that's kinetic energy. And that makes sense, right? That's the kinetic energy of that one. This is the horizontal kinetic energy of this mass due to the motion of the whole thing. This is kilograms meters per second times meter. This is meters per second. L times theta dots meters. So it's meters per second squared. That is energy. This is kilograms meters per second squared, meters squared per second squared, energy. This is potential energy. Okay, so at least it has all the right units. Okay, let's again do the x one first. So I'm going to do the partial of L with respect to x. And it's 0. There are no x terms in this. That's cool. Now the partial of L with respect to x dot. And remember the Euler Lagrange equation says the partial of L with respect to Qi minus the derivative with respect to time of the partial of L with respect to Qi dot is 0, where Qi was some generalized coordinate. Qi dot is the generalized coordinate with the derivative with respect to time, so it's the velocity. We use this dot notation, 1 dot for the first derivative, 2 dots for second derivative. You know, and I made a mistake. I actually do better when I make a video. I don't know if that may be surprising, but I'm speaking out loud. It's kind of like the rubber duck syndrome where it's not a syndrome. Strategy for programming. You have a duck there and you're talking to the duck, and so you're less likely to make a mistake or find something you did wrong. Okay, partial of L with respect to x dot. So I'm looking for all the terms with x dots, so there's that one right there. I'm taking the partial derivative. So the partial derivative, I just assume that I don't worry about the derivative of x dot, but then I get m1 x dot. M plus m2 x dot. Here's another one. I can just take the derivative of that. I get plus m2 L theta dot cosine theta. And there's no other x dots. Okay, so now I can take the derivative of this with respect to time the derivative with respect to time of the partial of L with respect to x dot is going to be equal to the derivative of this with respect to time, which is m1 x double dot plus m2 x double dot. Now here I have two terms that depend on time, theta dot and cosine theta, so I have to do a product rule. So let's do the theta dot first. So I get plus m2 L theta double dot cosine theta, and here's where I think I made my mistake before. Now I have to take the derivative of this, so I get plus m2 L theta dot. Now when I take the derivative of cosine of theta in here, I'm going to get another theta dot. So this is theta dot squared, and that's sine theta, but that's minus. The derivative of cosine theta is minus sine. Okay, so that's that. And this is all equal to 0 because the partial of L with respect to x is 0. So now I want to solve this for x double dot. So I get, I'm going to just move that to the other side and divide by m1 plus m2. I can do it all in one fell swoop because I like to live dangerously. X double dot equals, okay, so this term is going to be positive over there. It's going to be m2 L theta dot squared sine theta minus m2 L theta double dot cosine theta, all of that divided by m1 plus m2. Okay, so I think that's fine. Masses cancel. This is acceleration. Meters, radians per second. Quantity squared is going to be meters per second. And this is meters per second squared. Meters per second squared. So the units work. I'm just checking the units. Okay, so that's my x double dot. Now I need to go back up here to L and take the partial and do the theta dots. The thetas. Okay, so I need to take the partial of L. Let's just scoot this up. How's that? The partial of L with respect to theta. The partial of L with respect to theta. So let's look through what terms have theta. No theta, no theta. Here's the theta. So the partial of cosine theta with respect to theta is negative sine theta. So it's just going to be negative m2 x dot L theta dot sine theta. No theta. Here's another theta. And I'm going to take the derivative of that, so I get plus m2 g L sine theta. Meters per second squared, meters squared per second squared. Is that. And this is also, actually they both have energy. Meters squared per second squared. Meters, kilogram meter squared per second squared has units of energy. Just checking. I can't add two terms if they have different units. Okay, now I can go back up here and take the partial of this with respect to theta dot. Partial of L with respect to theta dot. No theta dot. No theta dot. Here's one. That's pretty easy. It's just one theta dot. So I get m2 x dot L cosine theta. And then here's a theta dot. I get power rule. So I get plus m2 L squared theta dot. Now I want to take the derivative of this with respect to time. d dt partial of L with respect to theta dot is going to be equal to, okay, here I have two terms that depend on time. So let's do the first one first. The derivative of x dot is going to be x double dot. So I get m2 x double dot L cosine theta. Now if I take the derivative of cosine theta, so I get minus m2 x dot L. I'm going to take the derivative of the inside, which is theta dot sine theta. Now I'll take the derivative of this. There's only one term, and it's going to be theta double dot. So I get plus m2 L squared theta double dot. And I'm going to set this equal to that. I can move this up now. Okay, so I get m2 x double dot L cosine theta minus m2 x dot L theta dot sine theta plus m2 L squared theta double dot equals negative m2 x dot L theta dot sine theta plus m2 GL sine theta. Okay, so I want to get an expression for theta double dot, but I have an x dot and a theta dot in here. So what I'm going to do is to take my previous expression for x double dot and substitute that in. Okay, so I'm going to go ahead and, oh, here I have, look at this, m2 x dot L theta dot sine theta, m2 x dot L theta dot sine theta. These two terms cancel. Yay. So I'm just going to put this in here. Okay. So I have I'm going to get two terms. So let's just do the first term. I get m2 times L cosine theta. Now I have all this stuff. So let's just take this first term. I have over m1 plus m2. And then I have m2, so I get squared. I have L squared. I have theta dot squared. I guess I should put it like that. And then I have sine theta. That's that first term going into here. Now I get the second term. I can start again with, I'm going to put the minus up front. So minus m2 L cosine theta. All of that over m1 plus m2. And then I've already got the minus. I get m2 squared, L squared, theta double dot, cosine squared theta. And that takes care of this term. These two are that when I substituted in the x double dot. And then I have this term plus m2 L squared theta double dot equals plus m2 G L sine theta. Unit check time. Okay, so this mass cancels one to that. So I have kilograms, meter squared, and this is 1 over second squared. So that's energy. Same thing for this, because this is going to have meters or radians per second squared times the same. It is energy too. And that is also energy, and that's energy. Okay, so at least they all have the same units. Okay, so now I want to take this and solve for theta double dot. So I'm going to move this term to the other side and factor out the theta double dot. Theta double dot times, I'll put it backwards, m2 L squared minus m2 squared L squared cosine squared theta, I factored that out, all of that over m1 plus m2, and then that moves to the other side. It's going to be m2 G L sine theta minus m2 squared L squared, I'm going to move the theta dot in, theta dot squared cosine theta sine theta, all of that over m1 plus m2. Okay, so that's good. I'm divide both sides by this. I could probably simplify, but I don't really care. Let's just check. Okay, so this is kilograms meter squared, so that's going to give units of energy 1 over second squared. This is kilograms cancel, so I get kilograms meter squared. Okay, so they have the right units. And this has kilograms, that canceled, meter squared. Okay, they all have the same units. So now what I can do, just like before, I can say theta double dot equals delta theta dot delta t. So from that, I can break this into small time intervals, and I can calculate theta double dot from here. This is done. All right, I just need to divide by this stuff. I'm going to do that in Python instead of writing it all complicated. I'm going to call this A, right? I'll just call it something A, and I can calculate that. So theta double dot is going to be, if delta t is very small, I get theta 2 dot equals theta 1 dot plus theta double dot delta t, and theta 2 equals theta 1 plus theta 2 dot delta t. So this is the Euler method, breaking in small time intervals, assuming theta double dot's constant to calculate the angular velocity at the end. Assuming the velocity is constant, calculate the position at the end. And then when I go to the next step, I can recalculate theta dot and then get this. And on top of that, I can do the same thing for x and x dot. And I did that before. The only difference here is I have different masses, so I can change things around, and I hopefully fix my error. But if I made a new mistake, hopefully some great commenter will find it. But let's go back to Python and see if we can make this all work. Okay, so I made this mistake before. I copied the code already. This is the previous code that I think has an error in it. And what I need to do is to change it up a little bit. So first thing I'm going to do is change this to, I need two masses, M1 and M2. And the masses canceled before. Okay, so I do have two balls. So let's just put it right here. Ball 2.m equals, I'm just going to call it M2 and M1. And my numbers are backwards, in fact. Oof. I put ball 2 at the bottom, and I called that one M1. I'm just going to, everywhere I see an M1 in my equation, I have to put M2. That's fine. M2 equals 1. It's 1 kilogram, very heavy balls. And M1 equals 1. So at least it won't matter at first. Okay. So down here, this is all my initial conditions. That's all fine. I'm not going to change that. I don't need to change the code for animation either. I do need to change this. So the first thing I'm going to do is say this. A equals. That whole term in front of the theta double dot, I'm going to call that A. And that's equal to, I'm just typing it for my equation. M2 squared, M2 times L squared minus M2 squared times L squared times cosine theta divided by M1 plus M2. So all that, since that whole term is A, now I can type my theta dot equation. I'm just going to delete this because I just don't want to make a mistake. So it's going to be equal to parentheses M2 times G times L times sine theta. I'm looking over there. Minus M2 squared times L squared times theta dot squared times cosine theta times sine theta, all of that divided by M1 plus M2. That's that second term. And then all of that I need to divide by A. See, so this is what's great about Python, right? I can break that into pieces. Instead of writing a complicated equation, I could just calculate in a different step. So now I have my theta double dot. Now I can really calculate my x double dot. I'm going to retype this equation because I don't think this is right. Actually, it's not right because I have the masses in there now too. So x double dot is going to be M2 times L times theta dot squared times sine theta. This all needs to be in parentheses. Times sine theta minus, not equals, minus M2 times L times theta double dot dd dot, which I just calculated, right? So I know what that is, times cosine theta. All of that divided by M1 plus M2. Okay, so then theta double dot, theta dot, x dot, they're all the same. They're all the same as what they were, and the animations are all the same. So it should work. It might not, but it should, okay, if I did make a mistake. And if I made a mistake, I'm cool with that. I'm fine. Okay, so let's run this. I didn't save it. Oh, my gosh. I mean, it looks like it works. Okay, so let's save it. Okay, so now what I want to do is, what if I make the mass at the top, which I'm calling M2. I'm going to make that 1 gram, right? In that case, the bottom mass shouldn't move quite as much. So let's make M1 0.01 gram. That's 10 grams. Okay. Now let's run it. I'm kind of excited. If this works, I'm gonna atone for my errors. Oh, I think I got those backwards. So let's make this one. How did I get that backwards? 1.001. Okay. That won. I won that. Let's go ahead, and since I am only at 20 minutes, let's calculate the center of mass and make that a point, just so we can see where the center of mass is in these problems. Okay, so I'm going to go down here, put it right down here. I'm going to say COM equals sphere. Position, okay, I need to calculate that first. So let's say RCOM, that's the center of mass, is going to be equal. How did I get those backwards? So M1, oh, M1 is the bottom one. That's right. RCOM is going to be equal to, we can calculate the center of mass as M1 times, parentheses, M1 times ball 2.pos. Remember, those are backwards because I'm a big dummy. Plus M2 times ball 1.pos, which I just call ball, divided by the total mass of M1 plus M2. So now I'm going to make this sphere, it's going to be at the position RCOM, which is the center of mass. The radius is going to be equal to 0.03. And the color is red. And make trail. Okay, so now that just calculates at one time. Down here, I need to recalculate that. So I'm just going to copy this code. After I update the positions of both balls, I'm going to recalculate that and then move the position. So com.pos equals rcom. Let's see what happens. Something bad happened. Oh, there it goes. Okay, I don't see anything because I think that the center mass is inside that sphere. It's because I had such a large thing. Let's go back to the masses being equal. And the center mass should be in the middle of the stick. Why is it so slow? I'm scared now. Okay. That's what I want to see. That's what I want to see, because one, I know the mass is in the center, the center mass is in the center of the stick, and it goes straight down, right? There's no horizontal forces on our system, so when it falls, the center mass can't change its horizontal momentum. It started at rest in zero horizontal momentum. It has to stay horizontal momentum, so it has to move straight down. That's exactly what should happen. Now let's just do for fun. Let's do 2 to 3. So let's just do mass 2 is, let's say half a kilogram, just to see what that looks like. The mass still stays in the middle. The center mass stays in the center. I like that. And I like this too. It's not really a curve. I mean, it's a curve, but it's not a circle, which is pretty cool. Pretty good. Okay. So I'm pretty happy with that. I could make plots of energy and stuff like that, but and I'd like to remind commenters for commenting. Thank you for fixing my errors. I'm pretty sure this is right. There still could be an error because sometimes things look right, but they could indeed be wrong. One thing I should do is, let's do this real quick. So let's switch this back to 1. And did I print out the time? No, it didn't. Let's print the time it takes to tip over. So down here, I did. I got T. I just didn't print it. Okay. Print T equals T seconds. Let's just see if I get a different value than what I got the last time. Why isn't it running? Oh, I didn't put a comma. All of that over not having a comma. That's great. Okay, T, comma. Got it. Okay, 0.736. Okay, where is my other, let's save this. No, that's, okay, I gotta open up the old one. So let's open up the old one. Let me go up here. My trinkets. Tip over, slip, I think it's this one. Yeah. Okay, and let's print out the time. And this is the one that I think is wrong. Okay, let's run this. So it is a little different. Okay, but still. Code down below, link to the playlist down below. If you find an error, let me know. Thank you for helping me. And the next one up is going to be the spring. I'll talk to you later.